For this last chunk of the notes, we're going to look at how different species will behave and their ability to influence whether a solution will be acidic or basic. So let's start off here. Cations and anions' ability to react with water. So the first one we'll look at here is the cation is from group 1. So again, think sodium, potassium, lithium, or it's a heavy group 2. Now, the reason we mention these, and when I say heavy group 2, typically we're thinking barium or strontium. The reason we mention these is typically these ions are going to separate and they're always just going to be hanging out in solution. Always, maybe not. But group 1s, absolutely. Sodium, potassium, lithium, they're always just hanging out in solution, not reacting, not doing anything. And typically these are going to do the same. They're not going to react with water in a way. So if you have these in solution, the other things you're going to have, I'm trying to think how else I want to add this in here. I'll do it this way. Ants, the anion, so the second part, the negative part, is the conjugate base of a strong acid. So remember, there's two parts to this problem. So a really classic example of this would be, I'll say the whole thing, HCl. So I've got the hydrogen, whatever. No, this is not a good answer. good example. I'm getting ahead of myself. Sodium and chloride. So here we go. We have a group 1, and chloride is the conjugate base of a strong acid, and we can think of several others. So let me just make this, I don't like the way I put this together. I'm thinking on the fly here. I'm going to put down chloride, nitrate as two good examples. So nitric acid, hydrochloric acid, we can come up with others. So having these kind of mixes in here, what would be the effect on solution? Is it going to be acidic, basic, or neutral? Well, these guys, think of it having the conjugate base of a strong acid, like HCl. Cl is not going to grab a hydrogen ion from water and form hydrochloric acid. It doesn't go in two directions. Remember, HCl only goes, as an example, in one direction. It doesn't form a solution of an equilibrium going back and forth. So if I have this in solution, it's not going that way. So this doesn't do anything in solution. Neither does the group 1. So what is this effect on solution? No effect on the pH of the solution. You're not going to have anything going on if you have just this and a group 1 or one of these guys. Okay, let's try another one. The anion reacts with water. It is the conjugate base of a weak acid. So if we go back and think, weak acids don't separate well. So when they form conjugate bases, they typically want to go in the direction. So if we write something like this, here's a weak acid, and I'll draw two arrows, one going this way and a stronger arrow going this way. So specifically what we're talking about here is this guy there. It is the conjugate base of weak acid, so it typically is going to go in that direction and grab a hydrogen from water, actually. So the second part to this is the cation is from group 1. So the group 1 I can ignore because sodium, lithium, potassium, heavy group 2. But the anion typically goes in this direction and grabs a hydrogen. Well, if it grabs a hydrogen from water, what is it going to do to solution? If it grabs a hydrogen from water, what is it going to be leaving behind? It's going to leave behind OHs. So OH left behind. And as a result of that, the solution will be basic. Let's do another one. You have a cation, and it's going to react with water because it is the conjugate acid of a weak base. And I'll give you 2 examples of that we can use. NH4 plus ammonium, and this is going to seem a little confusing. We'll come back around to that. Metals with high charges, so +2s a little bit, +3s even more so, not +1s. +1s, again, those are group 1s, so they don't really do that. So the way we can look at this one is, again, if we have the conjugate acid of a weak base, so if we have NH3 and it reacts with water, again, short arrow this way, long arrow that way, having NH4 plus hanging out in water. How do I want to do this? Let's do this, OH. It's going to very much donate hydrogen back to hydroxide and form this type of solution. Or, let me do it this way to give it a better emphasis. If it's just in water, it's going to more likely do this, where the hydrogen is going to be donated just into solution and give an H or H3O positive, having this scenario. So if this is what we're looking at, you are going to find a solution that is acidic. Okay, let's look at a couple examples. Let's do barium acetate. So we have to look at both of them. Barium is a heavy group 2. Okay, so typically those don't do anything. Acetic acid is not the acid, it's the conjugate base of a weak acid. So go back to your list that we just made up here. Conjugate base of weak acid typically reacts with water to form a basic solution. This doesn't contribute at all. So we will say basic. B. NH4 Cl. Let's look at both of them. NH4 plus is the conjugate acid of a weak base. So it's a conjugate acid. So typically that is going to donate as hydrogen and make an acidic solution. But what about this? This is the conjugate base of a strong acid. It's not going to do anything, so I can ignore it. This is the conjugate acid, which typically will donate its hydrogen because it doesn't dissociate well or doesn't absorb well in the other direction. So this one is actually going to end up being acidic. C. CH3, NH3, Br. Now this one may not be quite obvious, so I'll just tell you, if if I separate this off here, it's going to be a plus, which makes it look like this will be negative, this will be plus. Let's start here. Br is the conjugate base of a strong acid, hydrobromic acid, and this is an organic acid sitting here. So this is a weak acid. It's the conjugate acid of a weak base. So being the conjugate acid of a weak base, it is most likely going to be acidic. I would expect most of these are a little bit confusing to you, so you're going to have to go through it and have it make a little more sense, or of course ask me a question in class or during whatever online session that we have. Next one, we have potassium nitrate. Group 1, forget about it. This is the conjugate base of a strong acid, forget about it. So this is neither. Last one we have, E, we have aluminum perchlorate. Aluminum is a +3 charged metal, and we said earlier in just the last little bit there that this tends to be acidic. Perchloric or perchlorate ion is the conjugate base of a very strong acid, so that makes no contribution going in either direction. So this one actually ends up being slightly acidic. All right, I'm going to end here, and we'll have one little bit left on the last problem you have in your notes.